this is Dr. Muhammad, and this is another video under Engineering Mathematics topic. We are going to continue our talk regarding matrices, and today we're going to talk about linear homogeneous system. This is the first part of it, and we are going to talk about how we can use what we have learned up till now for solving the linear homogeneous system. Okay, let's go directly to an introduction for this linear homogeneous system way for the solution of these systems. First of all, we want to understand that we want to develop a method for finding all solutions of linear homogeneous system of n equations and m unknowns. Take care of this. First of all, we want to know why we have learned up till now all the matrices skills and manipulation that we have spent many videos before. The main reason is for today video, which is the solution of linear homogeneous system, and we are going to talk next time about the after maybe 2 videos we are going to talk about the nonlinear or non-homogeneous systems. So actually we want to see that if we have a set of n equations, as you can see here, and we have a set of m unknowns like x1, x2, x3 until xm. So we have a system. This is system of homogeneous equation, because in the right hand side of the equation there is 0. Okay, so this means that this is a system of homogeneous, linear homogeneous system that contains n equations and m unknowns, which is x1, x2, x3, x4. Okay, so the number of equations starting with 1, 2, 3 until n, where n is the number of equations, and the number of unknowns, which is x1, x2, x3 until we reach m. So we are horizontally moving with the number of unknowns m, and vertically we are moving with the number of equations n. That's good. Okay, the numbers inside the numbers here, which is a11, a21, a31, a41, and so on until an1. Okay, and also the numbers which is in the same equation, which is like a11, a12, a13, and so on until a1m. These numbers, these coefficients, we call it aij, are called the coefficients. We call them coefficients of the system, and we are going to put them in an equation. Okay, and this matrix form, it equals to ai and j. Ai and j means that it is the matrix of coefficients which containing, yes, all the coefficients a11, a12, as you can see, we put it here, and here we're going to have a21 until we reach to an1. Okay, and so on and so forth for the remaining. So we have this a, which we call it the coefficient matrix, and we denote it like this: a equal to, this is capital uppercase and bold, equal to a I of j, between parentheses, is the matrix of coefficients, Rho I, so whenever we are talking about rho I, okay, which is here also in the coefficient matrix, rho I contains the coefficients of equation I. So each row here contains all the coefficients that you can find in the equation number 1, for example, or equation I. Okay, and column J, and whenever we look to any column, which is, we call it column J, it contains the coefficients of what? Of the same unknown, which is xj. So we have I, which is indicating to the row, j indicating to the column. Okay, and this column, it means that all the coefficient of the same unknown, okay, which is related to xj, and this row, it is related to equation, okay, the equation I. So we're talking about equation I. So the row is an equation, the column means that the coefficient of one unknown. Okay, so this is the meaning of this system, and now we are going to deal with it in similar fashion of what we have dealt before with the matrices. Okay, now let's go, and we are going to define for each column. For each column we have like x1. If we go back here, the column here, okay, it is having all the coefficients, right? But actually we have like x1, x2, x3 and so on. They are the unknowns. So they are from x1 till xn, okay, from x1 to xm. So this means that we are going to put it in a matrix form or a vector form. We are going to denote it as x capital, which is the vector of the unknowns, x1, x2 until xm, okay, until xm. It is the number of unknowns, okay. And we are going to write the zero matrix, which is on the right hand side of the equation. It is going to be something like this. It is only zeros, okay, it is only zeros, and it is going to be with the dimensions n by 1, n rows by 1, because if you go back, you're going to find that our system is zeros here. So we're going to say that this is big zero here, which is, it is a vector. It does not have anything except zeros inside, and its dimension is n by 1. Okay. So now we know that we have x, we have O, which is going to be zeros, as I said here. So now we can write, then the system can be written as the matrix equation. We can put it in a matrix equation, which is AX equal to 0. Okay, AX equal to, this 0 means that it is the vector of zeros. This X means that it is the vector of unknowns. And this A, it is the coefficient matrix. So now we have a system of homogeneous equation. And instead of putting it in this clumsy form here, we can make it nicer by putting only in a matrix form, short and concise, right? Okay, now we want to solve this. Now we have transformed the linear homogeneous system to matrices system, and we are going to use our skills in manipulating matrices in order to find solution. So what is our main goal? Our main goal is to find what is x1, what is x2, what is x3, and so on. We want to know the values, or how much x1 would equal in terms of x3, for example, or how much x2 is equal to multiples of x3, and so on. We can like say that there is free variable, that we can define all variables based on it. Okay, so this is what we call the solution of the system. Okay, now we will develop the following strategy for solving this system. First, we will show that AX equal to 0, this is the matrices, take care we are talking about matrices, has the same solutions as the reduced system AR times X equals 0. What is this? We said that before, right? We said that. Do you remember AR? It is the reduced form. And we mentioned that for the reduced form, it is going to be obtained by some row operations. We can obtain this AR from the original matrix A. We are going to say today that in order to get the solution of this system, no need to go through this system directly, but we are going to change it to a simpler system, which is AR times X equal to 0, and this system is equivalent to the original system. And we are going to find that the solution of this simpler system is much easier for us than the solution of this original system. Okay, so we need to be sure that this system is equivalent to ARX equal to 0. Okay, and number 2, we will show how to write all solutions of the reduced system directly from the reduced matrix AR. We are going to find that it is very easy to the extent that no need even to solve the equation. We are going to look to the AR directly, and we can obtain the solution from the reduced coefficient matrix. Okay. And number 3, we will also use facts about vector spaces and rank to derive additional information about solution. This is the third thing that we are going to learn in today's video. Okay, now let's go to the first thing, and we are going to show the form or the first step, which we said before, which is the reduction, whether it would help us or not. The reduced form would help us or not. So let's have an example to explain it. Consider the simple system x1 minus 3x2 plus 2x3 equal to 0, and minus 2x1 plus x2 minus 3x3 equal to 0. The coefficient matrix here is going to be put here. We have 1 minus 2, 1 minus 2, and minus 3 and 1, minus 3 and 1, and 2 and 3. So this is 2 and sorry, minus 3. So we have, this is the coefficient matrix of this system. The right hand side is, as we can see, zeros. So it is linear homogeneous system. And our x capital, it is going to be, as I put it here, x1, x2, x3. This is the vector of the unknowns. Okay, so we are going to get our AR, how we can get the reduced matrix. Please revisit the previous videos. I think that you are trained well on how to obtain the reduced matrix. So now the reduced matrix from A, the echelon form, is going to be, after some row operations, this is the reduced matrix. As you can see here, 1, it is the leading entry. Here is 0, and the leading entry for the second row, it is 1 also, and everything is 0, and it is only 2 non-zero rows. Okay, 2 non-zero rows, and the third column, as you can see it here. Okay, the reduced system, now we want, as we said before, that AR times X equal to 0. We claimed that they are going to be the same as if that we have used the original matrix. Okay, so this is a kind of like verification, but this verification, it is understood. I mean that no need to go to the verification here, that you need to, or we need to say that yes, AX equal to 0, it is the same as equal to AR X equal to 0. So they are the same. We are going to claim this. The reduced system is, in this way, our reduced system. So we're going to multiply AR by X. This is our X. So our AR, which is this one, times X, which is X1, X2, X3. Then we put it in the form. So 1 times X1, right? So it is X1, 0 times X2, it is 0, there is nothing here. And then 7 over 5 times X3, which is plus 7 over 5 X3, equal to, yes, in the right hand side it should equal to 0 and 0, right? So as if that we are multiplying the AR times X equal to 0. This is our system. This is the homogeneous, linear homogeneous system now. If we assume that AR times X equal to AX. So, and the second line, we can read from it, 0 times X1, there is nothing here. And then 1 times X2, it is X2, minus 1 over 5 times x3 minus 1 over 5 x3 equal to 0. So now we have these two equations. As you can see here, we have x1 here and x3 here. We have x2 here and we have x3 also here. This means what? That x3 has been repeated in the two equations. This means that we can put x1 in terms of x3, right? And we can put x2 in terms of x3. Let's put it like this. So x1, rearrangement here, we're going to find that it equals to minus 7 over 5 times x3, and x2 also it equals to, from this equation, 1 over 5 1/5 x3. Okay, what is x3? It is one of the unknowns. We are going to call it as the free variable. Okay, we're going to call it the free variable. X is arbitrary, means that it is any number. It can assume any value, any number that we want. If we assume that x3 equal to 1, for example, then we can obtain the value of x1 and x2. This means that our solution space is based on one of the unknowns. Okay, all the unknowns x1 and x2, they are dependent on one variable, which is x3 here. Okay, it is x3. Okay, now let's go. So now we know that x1 is function of x3, x2 is function of x3, and x3 is arbitrary. We can give x3 any numerical value, and this determines x1 and x2 to yield a solution. That's right. It will be useful to write this solution as a column matrix. Commonly, we use this, what we call it, column matrix, as the way of representation for our solution. So we say it like this, that x, uppercase, bold, which is x1, x2, and x3 equal to x3 here as one variable. Output, we call it the free variable, okay, times, now we have, this is minus 7 over 5 here, x3 here, and x2 equal to 1 over 5 x3, so it is 1 over 5 x3, and here it is x3, right? So this means that x1 equal to minus 7 over 5 x3, and x2 equal to 1 over 5 times x3 here, and x3 equal to x3, right? So that's it. And then we are going to, in order to look neater and like nicer, we, instead of putting x3 as it is, we put it like alpha. It is only numerical value. Only we are changing the designation. That's it. Alpha is like, seems to be nicer, and it seems that any number that you are going to assume for alpha, x1, x3, and x2 and x3, they are going to have a value dependent on whatever that you are going to assume. Okay? Okay. This general solution of the reduced system is also the solution of the original system. In this example, the general solution depends on one arbitrary constant, which is x3. Hence, in a sense to be discussed, it is, we call it one-dimensional solution. So what is the meaning of one-dimensional solution? It means that we have only one unknown that is our solutions are depending on. So we call it one-dimensional solution. One-dimensional solution. Okay? So that's the case for us. If you want, you are free actually to look to the textbook if you want to be sure that AR times x equal to A times x equal to 0. You are going to find that the solution of this system, reduced coefficient matrix, equal to the solution of the original coefficient matrix times x. Okay, you can find this in the textbook, and if you want, you can verify it by yourself. I mean that you can solve the solution, solve the system by yourself and check it. Okay, check that this system, which is going back here, This is the system here. Okay. If you want to solve it, you can solve it in terms of x3 as you're going to find, and at the end you're going to find that x1 equal to this value and x2 equal to this value. Okay, you're going to find that it is the same solution. If you want, you just can you can put and substitute here. Put x1 equal to minus 7 over 5 x3 and put x2 equal to 1/5 x3 and substitute in this equation. You're going to find that it equals 0. So this means that it is true. Okay, there is a verification in the textbook or other textbook, but it is not important for you to know this verification. Just you can verify by this way, as I said, that you can solve it using AR, and then whatever that is going to be yielded at the end, take it and substitute in the original system. If it works, this means that AR times x equal to AX equal to 0. The solution for original system equal to the solution of the reduced matrix, coefficient matrix, times the unknown vector. Okay, now let's go to the next. Okay, let's go here. So in the previous example, x3 is called free variable. That's what I want you to remember. Free variable. Since it can assume any value, we call it free. This is why we call it free. Okay, it can assume, it's arbitrary. This means that it can assume any value. This example had one free variable, but the general solution of a system, which is AX equal to 0, might have any number. Okay, any number. So free variables occur in columns of AR that contain no leading entry of a row. What is the meaning of this? Here we are telling that there is a way that by a glance you can tell what is the free number of the free variables from the AR, from the reduced matrix. Look to the reduced matrix that we have in the previous example. We have a leading entry here, we have a leading entry here. There are two non-zeros. So, but we have something here. We do not have any leading entries here, which is, it's a column. Actually, whenever you see something like this, you can consider this like x1 here, x2 here, and x3 here. Whenever you see a column that does not have any leading entry, this means that its associated unknown is going to be the free variable. Okay, so we have here this column for x1, it is leading entry here, and this column, it has a leading entry here. So x1 and x2, they are like dependent, but x3, it is going to be the independent, the free variable for us. So if we have, for example, okay, free variables occur in columns of AR. So now it is again, we are looking to the AR that contain no leading entry of a row. Okay, no leading entry of a row. Okay, now let's have some examples so that we can understand what we have learned up till now. Okay, now let's have this example. Consider this system. We have a 3 by 5 system. 3 by 5, we are starting from x1, 2, 3, 4, 5. Okay, and this is the equation here equal to 0. We have the second equation. We have x1, x2, x3. We do not have a 4 and 5 here. And we have here in the last equation x2, x3, and x5. Okay, so now let's put the matrix of coefficient and define it. So here, our matrix coefficient, we have how many equations? 1, 2, 3. So we are going to have 3 rows. So we have 3 rows times how many unknowns? We have x1, x2, 3, 4, 5. So we have 1, 2, 3, 4, 5. We have 5 columns for 5 unknowns. We have 3 equations or 3 rows for 3 equations. This is a linear system, homogeneous system, because the right hand side is 0. So our coefficient matrix is looking like this. x1, 1 here, so it is 1. Here it is 1, so it is 1. no x1 here, so it is 0, coefficient 0. And then for x2 it is minus 3, and here it is 2, and here it is minus, there is no x2 here, sorry, there is x2 here, which is 1, so we have 1 here. And then for x3, 1, and here minus 3, and then minus 4, and so on. So this is the coefficient matrix, as you can see, 3 by 5, number of unknowns, 1, 2, 3, 4, 5. Okay, now you can stop the video and make the reduction of this matrix to obtain AR. So from A, please stop the video here and work out the reduced form of this original matrix by yourself and find whether that it's right or wrong here. When you look here, you're going to find that after reduction we have leading entry here, leading entry here, leading entry here. We have 3 non-zero rows. The first column, if we say that associated with x1, this one associated with x2, this x3, and then this is associated with x4, and this one x5. This column is x5. So if I am going to ask you which columns or which variables considered to be free variables in this system, so which one that you're going to pick exactly? That's right. It is x4 and x5. Why? Because they are having columns that do not have entry, or they do not have the leading entry on them. So we have x4 and x5. So what is the meaning of x4 and x5 to be variables? This means that x1 is going to be function of x4 and x5, and x2 similar, and x3 similar. They are going to be function in x4 and x5. Okay, x4 and x5, as we are going to see now. Okay, now let's go to the next part, which is the reduced system and finding its solution. So now our reduced system is AR. Already we obtained it from the previous slide. And our x, it is going to be the vector of unknowns, x1, 2, 3, 4, and 5, equal to the vector of zeros here, 5 zeros and 1 vector. Okay, now let's put our system. It is x1 minus 35, 16, AR. This is from the previous, okay? From the previous slide here, this is AR. So we're going to multiply AR by, this is x1, x2, x3, x4, and x5. Okay, and equate it with zeros. Okay. So whenever that we are going to multiply, so 1 times x1, okay, plus 0 times x2, which is 0, plus 0 times x3, which is 0 also, plus minus 35 over 16 times x4, plus 13 over 16 times x5 equal to 0. This is how we are reading after the multiplication to obtain the ARx equal to 0 here. So we'll put it like this. So we're going to find that x1 minus 35 over 16 x4 plus 13 over 16 x5 equals 0. Similarly for x2, we're going to find that we are reading from directly from yes, as if that we are reading from these two columns directly. Okay, so I can put it easy for you. For example, I can put x1 minus 35 over 16 times x4. Remember, this is related to x4, this is related to x5, plus 13 over 16 times x5 equal to 0, right? And similarly, I can put the second equation, x2 equal to, or x2, sorry, this is here minus here, so x2, it is going to be in a similar fashion reading from these two. Okay, so x2, we can put it like this, x2 28 over 16 times x4 minus 20 over 16 x5. Let's go back. 28, that's right, times x4, as we said here x4, here x5, and minus 20 over 16 times x5 here. And so on for the third also. We're going to read it directly, we're going to read it directly from here. So x3, okay, plus 7 over 16 x4 minus 9 over 16 x5 equal to 0, right? I just read this and this terms for x4 and x5 and equate it with 0. Here, that's equating it with 0. Then, if you look to the first equation, you're going to find that it's function of what? Here x1 and here x4 and 5. Similarly, x4 and 5, here 4 and 5. So we can put x1 in terms of 4 and 5 directly. So x1, rearranging it, x1, it is going to be function of x4 and x5, x2 similarly, x3 similarly, right? So this means what? As we have expected that x4 and x5, they are going to be x4 and x5, they are our free variable. Okay, they are our free variables. How we can tell this? Yes, from here, from the reduced matrix. Now we can get the benefit from having the reduced matrix. We can get the benefit of reducing our matrix. So all of these in leading entries, it means that x1 here or x2 or x3 is function of x4 and x5 here or here or here, right? So the reduced matrix is very useful for us to get the solution, okay, and to let us know which are the free variables. Okay, let's go to this. Now we have obtained in which x4 and x5, the free variables, can be given any values, and these determine x1, 2, and 3. Again, note that these two free variables are in the two columns of the reduced matrix that contain no leading element of any row, as we said, here and here. Remember that well. Okay. Now, what is the solution for us? What is the solution? We can get the solution like this, that x1 equals to 35 times alpha, where this alpha is going to be, if we're going to assume x4 to be 16 alpha and x5 to be 16 beta, okay, with alpha and beta, they are arbitrary numbers in writing, only any arbitrary number, okay, just to make it, as I said, to make it neater and looks nicer. Okay, so we're going to remove this. So this x4 and x5, okay, we are going to take x4, okay, over 16, for example. So x4 here, it is equal to 16 alpha. Okay, so that's it, because we want to get rid of this 16 here. So we said that x4 equal to 16 alpha. So this 16 would cancels this 16, and we're going to remain with alpha times 35 directly. Similar here, this is 35 alpha, and then the 16 is going to vanish after assuming x5 to be 16 beta. So we're going to find that 13 only is going to remain for us, 13 beta. Now it's better like this, like to say that x1 equal to 35 alpha minus 13 beta. That's easier and looks nicer. x2 in a similar fashion, it was going to be 28 alpha plus 20 beta, where that, as we said, alpha x4 equal to 16 alpha and x5 equal to 16 beta. Similar x3. Now what is x4? It is our assumption, 16 alpha. What is x5? It is 16 beta. So all of them, they are function of what? Alpha and beta. That's it. So these are the two variables from where we can tell them directly from the reduced matrix, which is going to be related to x4 and x5. Okay, now great. Let's go now to putting it in the what we call it the column Okay, it is better to put it in this form. We can say that this is the general solution now. So we're going to say that x equal to 35 alpha minus 13 beta. That's okay. But we can like separate them better. So we can put it in this nicer form. We call it in the column matrix. Okay. We are going to put alpha here and beta here. And we are going to make two vectors. First value here, 35, it is here. It is this number, 35. And then plus beta, which is, we have minus 13 here, which is, we put it here. It's only the same form of the vector, but we put it in this matrix, column matrix way. It is better actually to tell, because we do not want to have alpha, beta, gamma, and so on in the same line here. Just we want to look, whenever we look to the system, to the solution of this system, we will say, okay, that's good. We have alpha and we have beta, the free variables, and they are like numbers here. So we can say the dimension of this solution is 2. The dimension is 2, or it is a two-dimensional solution. Means that it depends on two free variables. Okay. This way of writing the general solution reveals its structure as being two-dimensional. Yes, whenever you see two vectors and two numbers here or two parameters here, this means that this is two-dimensional. If there is something else that I have add, for example, like gamma, and there is another vector, then it is three-dimensional. This is a better way for representation of the general solution of homogeneous system. Okay. Okay, there is a theorem here, you can find it in the book, which is let A, which is the coefficient matrix, to be n by m. Then the system AX equal to 0, which is the homogeneous, linear homogeneous system. And the reduced form of this system, which is AR times X equal to 0, have the same solution. This is the theorem, and you can find the verification in the book. Okay, really this is what we have tried by ourselves, and we found that it works. Okay, now let's go to the next part, which is another way for representing the solution. So if we have A, which is the coefficient matrix, to be n by m, then the set of all solutions AX equal to 0, okay, all solutions, forms a subspace of R to M called the solution space. We call it the solution space of the system. The dimension of this solution space, we can get the dimension of this solution space. What does the dimension means here? How many free variables are there? That's it. How we can get this dimension without going into the details of anything? We can put M, which is the number of, exactly, number of columns of the coefficient matrix, minus the number of non-zero rows of AR. Do you remember this from the previous videos? What is the number of non-zero rows? It is what? Exactly, it is the rank of the matrix A. Okay, so this is the rank of matrix A. This means that M minus the rank of matrix A would give us the solution, which is the dimension, sorry. Is going to give us the dimension, two-dimensional, three-dimensional, four or less. Okay, so this is what we call it the solution space of a homogeneous system. Okay, now you can find that the benefits of AR. Okay, AR is a great matrix for us. The reduced matrix, really great. We can tell directly without going into the details what is the dimension of this system based on the number of columns of the coefficient matrix and the number of non-zero rows, or the rank of matrix A. Okay. Now let's have an example and see how it works for us. Okay. Now we want to solve this system, which is, as you can see here, minus x1, x3, x4, and 2x5. So this is our system here. And the right hand side, all of it is zeros. and we can extract the coefficient matrix easily from here. So here it is -1, and after that here there is no x1, so it is 0, and here x1 is 1, so it is 1, and here x1, yes, -3, so we have -3. And in similar fashion you can get the numbers of all unknowns, and we arrange it in the column in this matrix, which we call it the coefficient matrix. Okay, done. This is very easy for us. Now it is routine manipulations yield in order to change this to AR. Please, as I said many times, stop the video here and try to work this by yourself, which is getting the reduced form of the original matrix. Okay, so I hope that you can get it. Stop the video here and come back and look to what you have done. Okay, now this is the reduced matrix. Looking deeply on this, if I ask you how many non-zero rows here, you're going to tell me 1, 2, 3, 4. So we have 4. This means that the rank of this matrix A is going to be exactly 4. And what is the dimension or the solution dimension of this system? Just looking from AR, you're going to find that we have here x1, x2, x3, x4. They are columns, and they are having what? The leading entries. This means that x1, x2, x3, x4, they are not free variables because they are having, their columns are having the leading entries. But when you go, you are going to find, yes, x5. x5 does not have leading entry. This means that it is going to be the free variable. Then our dimension, space, our solution dimension, we can obtain it just by investigation of the reduced matrix, or simply we can say it equals to m minus the rank of A. What is m? Exactly, here it is n by m, the number of columns, 1, 2, 3, 4, 5. So we have m5 minus the rank of A, which is the non-zero rows in the reduced matrix. We have 1, 2, 3, 4, so we are having 4. Then 5 minus 4 equals to 1. This means that the solution dimension is going to be 1, and we know well that it will depend on x5. Okay, why? As I said, from the reduced matrix, this column is having none or does not have or contain any leading entry. Okay? Okay, now it's clear for us. Now let's go to the remaining part. In this example, A has m equal to 5 columns and the rank is 4, as I said. So AR has 4 non-zero rows. The solution space is going to be 5 minus 4, which is 1. And what is the free variable? It is going to be exactly x5. x5 here, as you can see. All variables, 1, 2, 3, and 4, they are function of x5. They're going to be function of x5. How we can obtain this system? The reduced system, we call it the reduced system, reading directly from the reduced matrix. So I can put like this. This is here 1, and all of them, they are 0. Now you can understand why we were trying to make all other rows in the same column to be 0. To make it easy for us to say that x1 equal, or x1, it can, or x1, let's put it like this, x1 minus 9 over 8 times x5 equal to 0, right? And x2, like x2 plus 5 over 8, reading from here, x5 equal to 0. And then x4 or x3, similar, we're going to read from here, 9 over 8 plus 9 over 8, x5 equal to 0. And here this is minus 4, so x4 minus 1 over 4 times x5 equal to 0. Just reading from the reduced matrix, no need to go into the details, just reading from the reduced matrix, this is the reduced system for us. Now we can understand that x1 equal to x5 times 9 over 8. It's easy. We can rearrange the first one. x1 equals to 9 over 8 times x5, and we can do the same for the remaining. So we put it in this form. This is x1, x2, x3, and x4, and we put them in terms of x5. Then we have the values now for x1 and x2 until x4. So let's assume that x1 equal to, so we're going to put actually like x5, let's put it as a, let's put x5 equal to alpha, which is going to be like the number. As I said, it's only transformation of the designation. It does not have any impact on our mathematics. Okay, so just we put it in a neater form. So x1 is going to be 9 over 8 alpha, x2 equal to minus 5 over 8 alpha, x3 equal to minus 9 over 8 alpha, and x4 equal to 1/4 alpha, and x5 equal to alpha. Okay, this is the alpha. Sometimes we do not like the fractions here, like 8 in the denominator, for example. We want to get rid of this 8. Okay, so we say that instead of saying that x5 equal to alpha, we can say that we are going to put beta equals to alpha over 8. Okay, so this means that whenever you substitute here, you're going to find that x1 equal to 9 beta, and x2 equal to minus 5 beta, x3 9 minus 9 beta, and x4 equal to 2 beta, and x5 equal to 8 beta, right? Because beta equal to alpha over 8, and this one equal to alpha. So x5 equals to 8 beta. And then we like to put it in this form. So the solution, we put the solution in the column matrix. The column matrix, this solution is going to be x equal to beta, okay, times only numbers here. So this means that x equal to beta times this number. This means that x1 equal to exactly 9 beta. x2 equals to minus 5 beta. x3 equal to minus 9 beta, and so on. x4 equals to 2 beta, and x5 equal to 8 beta, as we put it here. Okay, so this is the way how it works. This gives the general solution as the set of all multiples of one solution, which form a basis for the one-dimensional, we are talking about one-dimensional now, solution space. Okay, one-dimensional. As I said, you can read it very easily from the reduced matrix. I'm sorry. So now this is the reduced matrix here. Simply we can say that this system is one-dimensional solution. One-dimensional solution. Okay, now let's go to the next part and let us solve another example to get familiar with what we have done. So we will solve the system. This is a very long system here. We are starting from x1 and we are going to end with x7. So we have the number of unknowns are 7. Okay, 7 unknowns. The number of equations, we have 3 equations only, as you can see. So our system, our coefficient matrix, extracting from the system that we have, is going to have the dimension of what? Exactly, we have 3 columns, sorry, 3 rows, and we have 7 columns. 1, 2, 3, 4, 5, 6, 7. Okay, so this is the coefficient matrix, and we can extract it easily from here. Please stop the video again and work the reduced form of this matrix. Okay, if you've done this, then we'll come back and we are going to find that the reduced matrix, if you have done it right, is going to be like this. One leading entry here, one here, one here, and then look here, we have, right, this is starting from x4 here because we have x1, x2, x3. seemingly from the reduced matrix, the first dependent variables, x1 and 2 and 3, they are not going to be free variables because they are containing the leading entry. However, x4, x5, x6, and x7, they are not columns that do not contain any kind of non-zeros, of leading entries, right? This means what? That we are going to have our dimensional, or our space dimension of the solution is going to be 1, 2, 3, 4. It is 4. Can you imagine? It is 4. This means what? It means that x1 is going to be represented as a function of x4, x5, x6, and x7. Similarly, for x2, it is going to be a function of the same set of variables. And x3 is going to be the function of the same set of variables. So we are having four free variables. 4 free variables. Okay, how we can obtain it? Just by inspection, or you can put it like this: m minus the rank, okay? M minus the rank of A. So m, it is the number of columns here, which is 7, minus the rank of A, 1, 2, 3. 3 non-zero rows, so we have 3 here. 7 minus 3, it is 4. So this is from the law that we have explained before. Okay. Now this is our solution, which is going to be, yes, we are going to put it in a form. This form is going to tell us what is the dimension. So we're going to put like x4 equal to alpha, x5 beta, x6 gamma, and x7 another delta, for example. Okay, so we have these variables. Then we're going to put them like this: alpha, beta, gamma, and delta. And we are going to put in what we call it in the matrix form, in the column matrix form. How we can put it easily without doing any problem? Just if you look here, you're going to find that this is x1 and 2 and 3, right? Starting from here, you can write the first interpretation for the matrix or the vector. So here it is -3, -9/5, and -11/5. Let's go back here. They are the same, right? Except that the sign is opposite. So that's true. You're going to take this and put it with negative signs here, and then for the remaining entries you're going to put, you're talking about x4 here, so this should be 1 because this is alpha, and we have assumed alpha to equal to be x4, and the remaining is going to be zeros. Okay, and the remaining is going to be zeros. So let's go and form this column, okay, vector from, sorry, let's go here, let's go from here. So I'm going to read it from here directly. So I'm going to put it like this: beta times, this is the column. So the first 3, they are going to be the same with opposite signs. So we have 3 minus here, so we're going to put minus, 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 and 67/7, sorry, over 7 here, and 178/35, and 36/5. Okay, and now I'm talking about beta, okay, which means that x5, as we have said. So we are going to have x4 to be 0, x5 is going to be 1, x6 0, x7 0. Okay, so this is the column vector that should be multiplied by beta. Okay, I think if you go, are going to be, it is going to be erased now, but remember it here. So it is here, as I said, with the different signs here, and then 0 here for x4, 1 for x5, because we are assuming beta equal to x5, as we said, and then the remaining are 0. Also the same here. This is very easy. We are going to put the same entries with the negative sign. Yes, exactly, from here. Okay, we have 0 here, so we have these values with the negative sign, take care, or the opposite sign, and then 0, 0, 1 here, and then 0. Okay, and for delta, similar fashion, take care of the opposite sign, and then 0, 0, 0, and 1 at the end. This is delta, which is already, we said it is for x7. So now this is what we call it the non-trivial solution. This is 1, 2, 3, 4-dimensional solution. This means that x1, x2, x3, they are dependent on x4, x5, x7, and x6 and x7. So that's the meaning of 4-dimensional solution. 4-dimensional solution. Okay, this brings us to the end of this video. Thank you very much for watching this video, and I hope that you can continue with the next video. Okay, thank you, and see you in the next one or the next video, where that we are going to take some examples only on what we have learned in the homogeneous, linear homogeneous system. Okay, thank you very much, and see you in the next video.